So we are going to be transitioning from talking about how Earth's climate has changed over the course of the Quaternary, meaning over the past couple million years, to focusing on how Earth's climate has been changing during recent history, namely during the periods where we have direct measurements or direct accounts of what the climate was like from human observation and science. As we enter this discussion, it's important to keep in mind a few takeaway points from the previous sections. First, we know that the Earth's climate changes over time. It's not static. Throughout the Earth's history, it has both significantly warmer and significantly colder than it is today. Second, climate change occurs as a result of shifts in the three major mediators of the climate, which are insolation, albedo, and composition of the atmosphere, especially greenhouse gases. So, when something causes these variables to change, the climate changes. The third is the average of weather. And when we are talking about changes to Earth's climate, we're talking about shifts that occur over long timescales, not just over a period of days, months, or even years. With that in mind, let's take a look at what temperatures have looked like on Earth in recent history. Many of the graphs that we have viewed up until this point span hundreds of thousands or even millions of years. This graph shows just the past 1300 years of temperatures, specifically in the northern hemisphere. This graph is constructed from a combination of proxy data taken from the ice cores and tree rings, as well as direct measurements from instruments, meaning thermometers, which when they became available. Each line represents a different set of temperature data collected somewhere in the northern hemisphere, and the black line represents one set of instrumental temperature readings. The dotted line that is set to zero running horizontally across the upper middle part of the graph represents the average temperature between 1961 and 1990 to offer a point of comparison. And this is a pretty busy figure to look at. So to give a more helpful picture, this figure gives you a sense of where the readings agree with each other. So darker zones on this graph mean that this is an area where the measurements taken in areas across the world closely agree with each other, and we can get a sense of what of the sort of average trends based on the composite of all the data sets taken together within this graph are. And the variations might seem very slight. You can see the temperature scale on the left is measured in Celsius, and the entire span on the graph is only about 2 degrees Celsius from top to bottom, which is about 3.6 degrees Fahrenheit. But it's significant enough that there are still some distantly warmer and colder periods in this 1300-year time span. For example, climatologists recognize a period referred to as the medieval warm period that occurred about 1,000 years ago, as well as a period called the Little Ice Age, which took place around 400 years ago. And again, these temperatures changes were relatively small. During the Little Ice Age, the temperature in the northern hemisphere were not even a full degree Celsius lower during this time. But based on what we know from human records of the time, the Baltic Sea completely froze over twice in the early 1300s. Farmland was destroyed by the expansion of glaciers in the Swiss Alps. Warm weather crops that had been grown in China for centuries, like oranges, were abandoned in certain provinces. So, small changes have big effects. We can also see how it was rare for temperatures in the past 1300 years to exceed the average temperatures that were measured between the years 1961 and 1990, which again represented by the black horizontal line. The exception to that is in the very recent history, which we know from the extremely reliable instrument readings of temperature taken since the late 1700s and early 1800s using thermometers. And if we zoom in on just this section of the graph that relies on instrument readings rather than proxy data, then we see a strong upward trend in temperatures. Temperatures in the northern hemisphere have climbed by about 1 degree Celsius since the year 1880, which again doesn't sound like a lot, But during the Little Ice Age, temperatures were only a fraction of a degree Celsius colder, and the Baltic Sea froze over. So small changes cause big effects. So this 1 degree Celsius uptick is cause for concern. And of course, the question that naturally follows once you realize that temperatures are increasing is, what is causing this to happen? Is this part of the normal variability in climate that we know Earth naturally experiences over long periods of time, where it cycles in and out of hot and cold periods? Or is the cause anthropogenic, in other words, caused by human activity? This is a valid question because we know the Earth's climate does change on its own without human influences. So, what do we know about how climate related factors have changed on Earth since the year 1880, over the span of this period where the temperature jumped by a degree Celsius? Well, as we learned previously, there are three major factors that determine climate: insolation, albedo, and greenhouse gases. Let's talk about changes that have occurred in each of these since the year 1880. And remember that we're only looking at a very short time span between 1880 and now, less than 150 years. The processes that we learned about in the Milankovitch cycle section, the cycles pertaining to Earth's orbital shape, its tilt, etc., these all shift over periods of time that last thousands to hundreds of thousands of years. Given that this astronomical cycles are so long, evidence shows that only a very small change has occurred in the amount of insolation hitting the Earth. Sunlight energy has increased by 0.12 watts per square meter since 1750. That's about 860-watt light bulbs per acre. This is not enough to bring about a temperature increase of 1 degree Celsius. In fact, it would take 8 times as much solar energy to bring about this big of a temperature change. So, while a small fraction of the temperature increase may be attributable to higher levels of insolation from the sun, this does not explain why temperatures have increased so sharply and dramatically. Okay, so if insolation isn't to blame, what about albedo? How has the Earth's albedo changed in the past 150 years? Well, remember that albedo has to do with the surface reflectivity. Different surfaces have different capacities to either absorb sunlight and retain their heat energy or reflect it back into space. And since the 1800s, significant amounts of deforestation have taken place across the globe, which increased the planet's albedo. This is because forests have a lower albedo, a lower reflectivity than other surfaces like cropland or bare soil or desert. You may remember seeing this time lapse of deforestation in Madagascar between 1984 and 2016, way back in chapter 1. And the table on the right is from earlier in this chapter. As you can see, coniferous or pine tree forests, as well as deciduous forests, both have an average reflectivity that is lower than soil grass or desert sand. They absorb more heat. And so the Earth has been transitioning to surfaces that should be reflecting more heat and causing a cooler climate. But we see the opposite effect in global temperatures instead. Excuse me. This figure shows you rates of deforestation between the year 1700 and the year 2020. The part of the scale that I've highlighted in the yellow bar covers the time period since 1880. So, as you can see, huge amounts of tropical and temperate deforestation have taken place, largely to be replaced with cropland and human development. So, albedo should be going up and up on Earth, which would cause temperatures to cool, but that's not what's happening. We also learned previously that volcanoes and asteroids can affect and have an effect on planetary albedo by ejecting ash into the atmosphere that blocks sunlight and causes cooling in the short term, and releasing carbon dioxide, which causes warming in the long term. It's fairly apparent that there has not been a barrage of asteroids hitting the Earth in the past 150 years, but what about volcanic activity? Well, the Smithsonian Institution's Global Volcanism Program is the leading authority on volcanic activity around the world. and their mission is to document and report information on volcanic activity happening on Earth over the past 10,000 years. And according to the Global Volcanism Program, there is no evidence that volcanic activity has changed over the past 150 years. It has remained about the same. This figure, published by the Global Volcanism Program, shows the rates of volcanic eruptions between 1800 and 2010. And at first glance, based on the top line, it might appear that volcanic eruptions are going up. However, according to the GVP, this trend is misleading. Humans are actually just doing a better job at keeping records of volcanic eruptions as time goes on. In the year 1800, humans were not as widely distributed across the globe, nor did they have the record keeping ability or international communication capabilities that we have today. As people have occupied more regions of the globe and as surveillance and communication technologies got better, so did the ability to observe and report more volcanic eruptions. The more meaningful data set to understand why GVP has concluded that volcanic activity isn't increasing is the bottom line. Which only includes volcanic eruptions over zero point 0.1 kilometers in size. Zero point 0.1 kilometers is 100 meters, a little smaller than the length of a football field. Eruptions of this size are considered large enough that people have done a good job noticing them and documenting them consistently over the past several hundred years. Whereas eruptions that are smaller than this may have gone unnoticed. And when we only consider eruptions that are larger than zero point 0.1 kilometers in size, there is not an increased trend in volcanic activity over time. So this means that volcanoes are not responsible for changes in the Earth's climate over the past 150 years either. The last factor that we have to consider is house gas dynamics. We know that insolation and albedo can't explain the global temperature increase observed in recent history. So the last variable available to us looks like greenhouse gases. And in the realm of greenhouse gases, we have seen that carbon dioxide levels have increased sharply in recent decades. We previously saw a figure showing fluctuations in carbon dioxide levels over the past 800,000 years. And this was largely based on proxy data from ice cores. But for the very most current part of this graph, the part that is closest to present day, we don't need to rely on proxy data. We have direct observations that come from atmospheric CO2 levels that have been measured extremely reliably and consistently at the Mauna Loa Observatory in Hawaii since the year 1958. And these measurements show that carbon dioxide has climbed from 315 parts per million, meaning out of every million air particles, 315 are carbon dioxide molecules, and now up to about 420 parts per million as of July 2023. The reason why you see a zigzag pattern in this curve is because of seasonal variations in the amount of CO2 that gets absorbed throughout the year, because the winter is snowy and cold in the northern hemisphere, and most of the Earth's landmass is in the northern hemisphere. And so there is a lot less plant life performing photosynthesis to absorb CO2. And then during the spring, when there is a burst in plant growth, there's also a burst in CO2 absorption. But despite this seasonal oscillation, it is very clear that there is an ongoing upward trend in the concentration of carbon dioxide in our atmosphere. CO2 is building up in the atmosphere. But where is it coming from? What is the source? The answer is fossil fuels, of course. CO2 is emitted when fossil fuels like gasoline, diesel, natural gas, and coal are burned for energy. And this is throwing the carbon cycle out of balance, releasing more CO2 than can be taken up by plants and other sources of carbon absorption, like bodies of water. You'll remember from our discussion of the carbon cycle that there is a natural give and take between the photoautotrophs, such as plants, that capture carbon dioxide from the atmosphere and incorporate it into biological molecules through photosynthesis, and then heterotrophs um, that consume those biological molecules and release carbon dioxide. And of course, when organisms break down their bodies, decompose and release carbon dioxide into the atmosphere as well. But historically, these processes generally strike a balance with each other. The CO2 that is entering the atmosphere should be roughly the same that is being drawn out of the atmosphere if you want the levels of this greenhouse gas to remain stable. For the past 150 years, though, the cycle has been thrown out of balance, where we're actually taking fossil fuels, which are the carbon storage of the earth for millions of years, and over a short time span, putting them into the atmosphere. You'll remember from our discussion of the carbon cycle that there is a natural give and take here. Um, and we can see this again here where we have um, CO2, carbon dioxide, interacting with water through the process of photosynthesis to create glucose and oxygen. And that glucose and oxygen can be um, well, the oxygen can be used to oxidize the glucose, and that creates carbon dioxide and kinetic energy that are used by those heterotrophs. And then that process is then repeated again. And this is because fossil fuels represent a very, very significant carbon source. Do you remember when we talked about bog bodies and ice mummies? These were examples of cases where sources of organic carbon containing molecules fell out of the carbon cycle and didn't fully decompose. They were just frozen in their state, existing beyond the normal forces that convert carbon and from one form to another. This was true of fossil fuels as well. Because remember, fossil fuels are the remnants of dead organisms that never fully decomposed and became trapped deep underground. They fell out of the carbon cycle. They've not been a part of the carbon cycle for hundreds of millions of years and have just been sequestering large amounts of carbon underground. And now we are pulling them out of the ground and burning them. When we burn fossil fuels, this is essentially an accelerated version of the decomposition process. We're looking at hundreds of millions of years worth of ancient trees and animals decomposing extremely rapidly, all at the same time when we use fossil fuels. It's no wonder the cycle is out of balance and carbon dioxide is accumulating. By one estimate, which is depicted in this illustration, there are over 10 times more gigatons of carbon dioxide sequestered in fossil fuels than are currently in our atmosphere. Obviously, if we were to dig and burn all of those, it would enhance the greenhouse effect to a degree that would be totally devastating for the planet. To give you a bit more perspective on how far out of balance fossil fuel emissions are with other processes, this figure shows your carbon dioxide emissions from the year 1750 onward from two sources, fossil fuels and volcanoes. Volcanoes is the light purple line that you see steadily just barely hovering at the bottom of the graph. And fossil fuels is the greenish line that you see shooting upward by several dozen billion metric tons. So clearly, carbon dioxide output from fossil fuels far exceeds what would be released into the atmosphere through natural processes. The climate system is being pushed out of balance. The greenhouse effect is becoming stronger, and this is what explains the 1 degree Celsius uptick in global temperatures over the past 150 years. And the fact that temperatures are continuing to rise at this trajectory, as this trajectory continues, in the next section, we will talk about the effects that our changing climate is having on the planet, and also the forecast of what things will look like as climate change continues.